Okay, today's T-notes will be on 5.4, magnetic effects of electric currents. We will be discussing magnetic field and magnetic force. Let's go ahead and begin. Electromagnetism is the phenomena where magnetic fields are produced when charge moves in a circuit. It deals with electromagnetic forces, which is an interaction between electrically charged particles. Magnets have certain characteristics. One characteristic is that all magnets have two poles. We call one end of the magnet north and the other the south pole. If you were to break a magnet, this would produce two new magnets that would each have a south and a north pole. We would have no magnetic monopoles, where if you were to break a magnet and you would only have a south pole. Opposite poles attract, and like poles repel. This is also similar to how charges interact. We have experienced this when we have placed two magnets together. Below we see two south pole ends repel each other, two north pole ends repel each other, and when opposite poles are near, they are attracted to each other. We can magnetically induce an object by placing the magnet near the material. When this happens, we say that the material has induced magnetism. Below, we have a magnet near a metal paperclip. The paperclip becomes a magnet with the north pole near the south pole of the magnet, and the south pole is furthest away. There are two different kinds of magnetism when we're talking about magnetic induction. The first one is hard magnetism. Hard magnetism occurs when a material becomes permanently magnetized. These are described as being magnetically hard. This is how magnets are made, and these are often alloys of iron, such as steel, but nickel and cobalt are other examples. These are the only pure metals that can be turned into a permanent magnet. Below is a picture of a steel paperclip that is magnetically induced, and when it is taken away from the magnet, the steel paperclip retains its magnetism. We call this hard magnetism. Soft magnetism is where induced magnetism on a material is easily achieved, as seen here with the iron nail that is close to the magnet. It obtains magnetic qualities. However, when the material is pulled away from the magnet, it quickly loses its magnetism. Similar to electric charges having fields, magnets also have fields, and these are called magnetic fields. They are represented by lines that are drawn from the north-seeking pole to the south-seeking pole to show the direction a north-seeking pole at that point would move. Below we see a magnet that has two arrows like the needle of a compass. The north pole is red and the south pole is in blue. If the magnet were placed near the north-seeking pole of the larger magnet is located here, the north-seeking pole on the needle would move away from the north pole of the larger magnet. This movement is shown as the lines moving outward. When the magnet is moved up here in this location, we can see that the north-seeking pole of the needle, that is red, is moving away from the north, and the south part, the north-seeking pole of the needle, again points away from the north and is attracted to the south-seeking pole of the larger magnet. These arrows are shown going from left to right. If the magnet is moved to the south-seeking pole of the large magnet, the north-seeking pole of the needle is attracted inward. The arrows show the inward pull of the north-seeking needle. A second characteristic of magnetic field lines is that they never cross. Also, if the lines are closer together, the field strength increases. You can see that closest to the north-seeking pole on the large magnet, the lines are closer together than on the sides, specifying that the field strength is strongest closest to the pole. The last characteristic is that field lines act like an elastic thread, and they are as short as possible. So you don't see these field lines all the way out here because they are being attracted, so it is as short as possible from the north to the south poles. The Earth's magnetic field also has poles, north and south. Due to the interactions made on magnets interacting with Earth, we can think of the planet as having a bar magnet inside. It was decided that the north magnetic pole is located here, and the south magnetic pole is located here. Notice how the north is down here, which may be backwards to what we might think it should be. The north magnetic pole is the south geographic pole. The south magnetic pole is the north geographic pole. Now, let's look at a compass. A compass needle is just a narrow, thin bar magnet that is balanced on a pin and has a north pole labeled N and a south pole labeled S. We know the Earth's north magnetic pole pulls at the south pole of every magnet in the world because opposite poles attract each other. So when you hold a compass level, the north of the compass needle points to the south magnetic pole, which is known as the north geographic pole. Likewise, the south of a compass needle would be pulled towards the north magnetic pole, which is known as the geographic north pole. When a wire has a flow of charge, magnetic fields are produced. We represent these fields as lines, similar to electric fields. Here we're looking at a current of a straight wire. Below we see two diagrams of wires that have current flowing. In the first diagram, you see a gray circle with a dot in the center. This dot communicates that the current is flowing out of the page or towards you. The magnetic field lines are shown going around the wire in a counterclockwise fashion. In the second diagram, the X inside of a circle tells you that the current is going in the opposite direction, with the magnetic fields going clockwise. One way to remember the direction of current with the symbol of the dot or the X is to imagine if it was an arrow that is either coming towards you or going away from you. If an arrow were to approach you and come towards you, then you would see a point or the tip of the arrow. If the arrow were traveling away from you, you would see the tail of the arrow, which looks like the X mark. There is a way to remember the direction that the magnetic field is moving, which of course is dictated by the direction of the current. It is called the right-hand corkscrew rule. Take your right hand, make a fist with your hand, and extend your thumb up. The direction of your thumb is the direction of the current. The direction of your fingers and how your fingers are wrapped shows the flow of the magnetic field. Here you can see the current is moving upwards, and the fingers are in the counterclockwise position, which is the direction of the magnetic fields. The diagram that corresponds with this is shown below. So here we have counterclockwise direction for the magnetic field, and we have the current coming up or towards us. One common and important magnetic tool is the solenoid. A solenoid is a coil of wire wrapped tightly around a cylinder. When a current runs through the wire, as seen here, the current is going in and around and then comes out this direction. A strong magnetic field is produced. This magnetic field can be seen here with the arrows coming in and a little bit of a loop back from the north to the south poles. The solenoid is given magnetic properties as if it had a north and a south pole. Using the right-hand rule, you can determine the direction of the magnetic field. The field lines within the coiled region are parallel and closely spaced, showing the field is highly uniform in strength and direction. Strength of the field diminishes with distance from the solenoid, which can be seen here because the distance from this line to this is much larger than the field lines inside the solenoid itself. The direction of the magnetic field depends on the direction of the current. Outside the current, the magnetic field is small. This is a simple way to produce a strong magnetic field. A solenoid can be used to convert electric currents into mechanical motion and force. For example, a switch. The solenoid can be turned on and off at will and acts in some ways like a permanent magnet. Here we see a diagram that is showing the direction of the current and the way that it is flowing. So here we show that the current is coming out, but then going back into the page, going out and coming back into the page. The magnetic field is shown in blue arrows. If we wanted to increase the magnetic field, we could increase the current in the wire. We could also increase the number of turns per unit length of the solenoid, or how many times the wire is wrapped around the metal rod. We could also add an iron core inside of the solenoid. When two wires are near each other and are carrying charge, there is an interaction between the magnetic fields. If you had two wires, for example, whose current was flowing in the same direction, the wires would attract each other, so the force would go inward. Because of this attraction, the magnetic field lines from the foils combine to give a pattern in which field lines loop around both the foils. When the currents are in opposite directions, as seen here in this part, one is going up and the current is going down, we get different field patterns. Now the field lines between the foils are close together and in the same direction, which represents a strong magnetic field. All right, so when there are magnets, we know that there is a direction of the magnetic fields. We also know that when a charge moves in a current, there is a direction for that current. And when a charge moves through a current, this also produces a force, which also has another direction. We have to have a way to remember which direction everything is going. One way to determine the force acting on the wire given the current and the magnetic field, we can use Fleming's left-hand rule, sometimes also called the FBI gun. If you were to make a gun with your left hand, as shown in this diagram, the thumb would represent the force acting on the wire. The index finger would indicate the direction of the magnetic field, which is abbreviated as B for magnetic field. And the middle finger points in the direction of the conventional current. Now remember, conventional current goes from positive to negative. When you line up the fingers in the correct directions of the current and magnetic fields, you can determine the direction of the force that is acting on the wire. Look at the diagram below. There are two magnets. Here's the north end and here's a south end. There is a current that is running towards us or out of the page. If we were to make our left-hand FBI gun, we know that the magnetic field is going from left to right in this direction. We also have the current with our middle finger running out of the page or towards us. Because we notice that the thumb is pointing up, we can say that the force acting on the wire is an upwards force. All right, so here's something for you to try. Which way will the wire be pushed, given that the red is the north of the magnets? We know that the direction of the conventional current is going from positive to negative. So if we make our FBI gun with our left hand and point the middle finger in the direction of left to right, we know that the direction of the magnetic field is from north to south, which is, in this case, in this direction of the black arrow. Our index finger would point in that direction. This places the thumb into the paper, and thus our force that is acting on the wire is into the paper. Now, when a force is experienced by placing a current in a magnetic field, this produces what is known as a motor effect. If we imagine a magnetic north and south pole near each other, here's the north and here's the south parts of the magnets, there is a magnetic field between them, and that is going in the direction from north pole to south pole, so we got a left to right motion of the magnetic field. Now let's run an electric wire through this field, and let's say that the current is flowing away from us. Because the moving charge within the wire creates a force, this wire would experience a downward force along the entire length of the wire. This is determined by the left-hand rule. If you point your middle finger in the direction of the current, which is going away from us, the index finger is in the direction of the magnetic field, which is from left to right, and you'll need to flip your hand in order to achieve this position. Your thumb would be pointing down, which says that the force emitted on the wire is downward as a result of the charge moving through the magnetic field. Now, let's take the same concept and apply it to a loop of wire, or a circuit. Within this loop of wire, the current is coming in from one end and exiting from the other end. So we have the current moving in one direction through the magnetic field and in the opposite direction in the other part of the wire. The wire will experience force in opposite directions, and you can test this by using your left-hand rule. The force that would be experienced would be downward over here, and it would be upward over here. This would then cause the loop to rotate. This rotation is called the motor effect. We see motors in any machine we turn on, and some parts of it turns. Here are some examples of motors. This is a very simplified version of the mechanics behind a motor, and it is more complicated. But the point is that you put current between a magnetic field and the wire circuit rotates, and this is called a motor effect. Another thing to note is that the direction of the current must be reversed every half turn. Otherwise, the coil is going to come to a halt. This is achieved by using a commutator. The size of the magnetic field, denoted as capital B, depends on the size of the force on a wire, as well as the length of the wire in the field and the current in the wire. The equation is represented below. B equals F divided by IL, where B is in Tesla, and Tesla can be broken down into these units of measurements, where F is the force in newtons, I is the current in amps, and L is the length in meters. If we were to solve for force using the equation from the past slide, we would get F equals BIL. And this would be for current and wires that are 90 degrees to each other. For currents and wires that are at angles with each other, we would use the following equation of F equals BIL sine of theta. So here we have the equation from the last slide for when currents and wires are at an angle from each other. Because the current is the result of moving charge, F equals BIL sine theta is written in terms of current. We can use this equation of current where I equals QT. If we sub this into the equation, we get F equals B times Q divided by T times L sine theta. We know that the speed is the distance divided by time. And here we have L and we also have T. So if we move these two together, we know that L divided by T is the speed, so we can go ahead and substitute that, and we get this new equation, which is in your data booklet, F equals BQ V sine theta. This new equation shows that the force acting on a charge Q moving at speed V at an angle theta to a magnetic field of strength B. Here is an example. Calculate the force on a power cable of length 200 meters, carrying a current of 200 amps in a direction north, 300 east, at a place where the horizontal component of the Earth's magnetic field is 10 to the negative 5 Tesla. Go ahead and pause the video and start it back up when you're ready. Okay, so with this one we are using this equation here when we plug in our magnetic field and we have our current. Here is our length and we have the angle that we were given. When we plug all that in, we get an answer of 0.35 newtons. All right, we've made it to the end of our T-notes. Here is the first of 2 practice problems, and here is the second. Okay, be ready to use this information in class, and thanks for watching.